Okay, so what do you think would happen if the paddle were moving up and down at a different rate? Would it change the speed of the waves? Well, I can alter the rate of the paddle using this control here. So first of all, if I slow it down, you can now see that the wave crests are further apart. The wavelength is longer, but they're still travelling at the same speed along the tank. Alternatively, if I increase the rate at which the paddle moves up and down, now the wavelength's much shorter, but again the waves are travelling at the same speed down the tank. So the speed of the waves is independent for any particular tank of water. Let's take a look at this using our graphical representation. This is the original displacement against distance graph of the water surface. With the digital clock, you can see that the wave takes 2 seconds to travel a distance of 1 wavelength. So the period of this wave is 2 seconds. This means that only half a cycle of the wave passes by a fixed point in 1 second. If the rate of the paddle, and hence the rate at which the water moves up and down, is now reduced, by a factor of 2 say, the wavelength becomes longer, as we saw in the tank. Since the speed of the wave is unaffected, it now takes 4 seconds to travel a distance of 1 wavelength. That's only 1/4 of a complete cycle passing by each second. On the other hand, if the paddle moves up and down more rapidly, the wavelength becomes shorter. In this case, the wave takes only 1 second to travel a distance of 1 wavelength. So with the paddle oscillating like this, 1 complete cycle goes past every second. The number of cycles passing any point per second is known as the frequency, and it's equal to the reciprocal of the period. F equals 1 over t. If the period is 2 seconds, the frequency must be half a cycle per second, and so on. So you now have two relationships that are true for all waves. Speed equals wavelength over period, and frequency equals 1 over period. Expressing the right-hand side of the first equation as 1 over t times lambda, and substituting f for 1 over t, gives the fundamental equation of wave propagation. Speed equals frequency times wavelength. Frequency, the number of complete cycles that pass a fixed point in 1 second, is measured in hertz. And at the moment, the paddle's oscillating about 6 times a second, so that's a frequency of 6 hertz. Now, if I double that frequency to about 12 hertz, that means that the frequency of the water waves is about 12 hertz, but the wavelength has halved, so the speed remains the same. And if I were to decrease the frequency again by a factor of 2, then the wavelength would double, and once again the speed would remain the same. This illustrates the important result that the frequency of a wave, multiplied by its wavelength, gives a constant number, the speed of the wave. So a long wavelength corresponds to a low frequency, while a short wavelength corresponds to a high frequency. Although the speed stays the same at different driving frequencies, it does depend on things like the geometry of the tank and the nature of the fluid through which the wave travels.